Hello, everyone. This is Kyle Welch with RCR Wireless News. I want to thank everyone for attending Mobile Interference Hunting, a Unique Approach, presented by Anritsu. Our presenter today is Mark Heimbach, Senior Product Manager at Anritsu. At this time, I'd like to turn the presentation over to Mark.
Thank you, and thanks everyone for attending the webinar. I'm going to be talking about a new approach for interference localization, how to most efficiently do an interference hunt. And before I get to that, I think the overall theme of the talk will be how do we find interference in the most efficient and most efficient way possible. So really to address this question, we'll break down the interference hunting process into a series of steps. The first one being, how do you know that the interference exists in your network? Well, obviously you might have a situation where there's low data rates or dropped calls, but having low data rates and dropped calls does not necessarily mean there's interference. There could be a whole host of different problems. So you need some good way to efficiently identify that the problem is caused by interference, obviously before you start your interference hunt. And then you look at what are the symptoms, and basically you drill down into the cause of interference. And that could be a whole host of different types of problems. And we'll be touching on some of these issues and look at some of the more prevalent types of interferers as we go into our discussion. The other issue is to look at where approximately the interference is being generated from. So it could be near or far. And one of the main issues that you need to deal with is to be in close enough proximity to that interferer where you can actually see it. And by seeing, I mean you're close enough to see it on a spectrum analyzer. So you need really a system to address all these issues, to be really cost effective and efficient. And then also you need some way to look for clues. Is the interference in band, is co-channel, out of band, adjacent channel, modulated? Very multitude of different types of interference. So we'll be touching on each of these as we look at the best way to hunt interference. So the agenda, we're going to be starting and looking at things to consider. What are the common interference problems that typically people see? We'll look at some of the traditional methods of interference hunting. One basic way is to triangulate interferers using directional antennas, and then look at a new approach or a mobile approach for interference localization. And specifically, we'll be looking at power of arrival techniques in order to do this efficiently and most cost effectively. So I have one slide here talking about some market trends. So we know, interference mitigation will really be a growing requirement in the market, particularly with the advent of LTE. There's the expectation from customers that they want high throughput and good quality of service. So we know that a lot of the cellular carriers and operators will be taking interference more seriously as we go into the future. So who's concerned about interference? Well, really just anyone that operates anything wireless. Telecom or cellular operators, government regulators, contractors that work really for all of the above, public safety, homeland security, police, fire, broadcast, AM, FM, TV, satellite operators, and so forth and so on. So there's a lot of people out there that need to be concerned about interference, and specifically how to mitigate that to have a good and reliable network. So we look at starting the interference hunt. So what's the first thing that we do? Well, one, we need to verify the existence of an interfering signal. And is it really an interferer that's causing a problem, or is it something else? So you can view the interferer on the spectrum analyzer, and I have a little chart on the bottom right. And we'll look at some of the parameters of spectrum analyzers. What a good spectrum analyzer is for this type of application. But in general, you do need a good noise floor. So if you want to see low-level signals, if you're far away from the position of the interferer, you have to have a good noise floor. and good resolution in order to be able to quote unquote see the interferer. And then you want to be able to estimate the interferer position. So there's different methods that can be used to do that estimation. So reasons to suspect interference. Well, they could be a lot of different reasons. User complaints, which is really for an operator the last thing that you want to hear about. When you look at interference, you really want to look at or know that there's interference before you start hearing complaints, if at all possible. You're looking at maybe some network statistics or KPIs. These are key performance indicators that are generated by the firmware in the cellular system that indicate different types of faults or issues that operators need to be concerned about. One of those might be a number of job calls in a certain sector. Could be a reason to suspect interference. But again, it doesn't necessarily mean you have interference. It means you do have a problem, but it could be things like passive intermodulation or PIM. It could be a network problem, a firmware problem with the network hardware. A lot of different problems can cause these interference issues. So you really need to verify the interference, and one of the best tools to use for that is a spectrum analyzer. So one method is that you can take a spectrum analyzer and check the interference if this is a cellular system at the base station. You could look at the noise floor from the receive level by looking at redundant ports. And many cell systems, in terms of the network equipment, will have redundant receive ports. So there's not only the master receive, but there's a redundant port that you can tap into that's wired to an antenna. So you're basically seeing everything that the receive system sees. And then you can identify, is there something out there that shouldn't be there? And how do you know it shouldn't be there? Well, there's various tables, databases that the FCC provides as an example, or it could be obvious that something is there that should not be present. So that's one method, but all base stations do not have redundant ports. There's different equipment vendors that may not have something that's readily available, and also in some situations you might have the redundant port located on an antenna tower for remote radio heads. You can also tap in that way, but again, it's expensive. You have to climb the tower, and depending on the situation, that might not always be feasible. So another way you can do it is actually just drive to the sector where the interference is suspected. In that type of situation, you may have indicators, from your KPI that it's in this at this base station area and in this sector. You have a 3 or 6 sector system, and then you have at least a good idea of the geographic area where the interference may be identified. And then you can also look at the signal. What kind of interference is it? You can look at the bandwidth as an example, modulation type. And this is applicable, particularly in border situations where you may have other, say LTE or WCDMA signals, and you can actually identify the modulation. I've been on a lot of hunts in Southern California, for example, where there's, between border from the U.S. and Mexico, or also a border with Canada, you may have other cell systems that, different operators in different countries that may be touching on the frequencies in which you're operating. So that's a good way to identify, the type of interference and generally where it's coming from. Audio is another way if you can demodulate it. It could be, potentially a harmonic for some lower frequency audio signal, for example. And then, as I mentioned, you can determine, which signals do not belong in that spectrum. And there's a little diagram on the bottom there. The interferers can really be off-channel or on-channel, as long as they fit within the filter bandwidth of the receive system. They can be generated in other channels and appear on the channel that you're looking at. So it's another thing that you might want to consider. So another piece of this is you want to note the interference characteristics. As I mentioned, it could be a wideband or broadband. Another characteristic, it could be pulsed or periodic. And we see this a lot with radar types of signals, where it has a duty cycle. It may be on transmitting for 1 second, for 1 second, and then be off for 10 seconds, and then come back on. or it could have a variable duty cycle. So you need to have a way to find these pulse signals, and then in a little bit I'll talk about how we can tweak a system in order to be able to find these types of pulses. And some of these pulses can be very fast, so we have some kind of receiver-like modes that we can use in a spectrum analyzer using fast Fourier transforms, catching large bandwidth simultaneously to be able to identify very, very fast pulsed signals. And and this is quite common, does the interferer vary with frequency? And there's a spectrogram that's shown on the bottom of the chart, and you can either have a 2 or 3D spectrogram. Here we're showing a 2D, with frequency on the X or horizontal versus time. And you can see the little squiggle there, and showing that this frequency is probably not very stable in frequency over time. And on the bottom you see kind of a third dimension of amplitude. And you can see, you can look at the actual level of the signal in this spectrogram combination. And for this kind of measurement, I'll get a little bit ahead of myself here. You really need to do a channel power measurement. So if you're doing a zero span or very, very narrow band and the frequency is drifting, you're not going to see it, you're not going to catch it as you do your interference hunt. So it's absolutely essential that you have a bandwidth that is at least as large as that frequency drift. And we've seen from our experience, and we need to incorporate in the systems that we develop for interference hunting a good channel bandwidth measurement. So some of the spectrum analyzer tools that we're looking at and looking at like pulse signals, and when I mentioned 10 seconds or radar type signals, that's one type of pulse, but you can look at pulses that exist over a longer time frame. And one of the things you can do is you can set up a spectrum analyzer remotely, hook it to Ethernet, and look at the time periods when a pulse may violate a certain threshold. You could actually have very sophisticated limit lines or just a single limit line. It violates a threshold, you record the time, and then you can identify certain kinds of patterns for the interferer. And so one of the things I mentioned is long-term monitoring. You can look at tools where you can view the historical pattern of interference. So one example is you leave this system out over many months, and you can identify something that may be periodic over a long time duration. And one of these things we've seen is actually quite prevalent is that if you're looking along the sea coast, you see a lot of problems with ships coming in. It could either be government, Navy vessels coming to shore. It could be tourist cruise lines. And you see these signals maybe pop up every few months, and then they're gone after a couple of weeks. So the only real way to identify these kinds of interferers is to have a kind of a long-term system where you're probing and looking for patterns. And then, once the interferer pops up, then you have a good clue that, maybe this interferer is something you want to look at. And if you're on the coastline, a ship that might be at port. So the other issue is it could be daily or weekly. Other examples we've seen that, maybe an interferer just pops up on Sunday. We've seen this in one case where a church was using a wireless microphone, and every Sunday the adjacent network system was having or dealing with interference. So it gives you different clues to look at and patterns, so that even before you go out, you have some idea of what you're looking for and where you're looking for it. So what I'll do is I'll talk about some of the examples of interference signals, and what I'm going to talk about is the most prevalent interferers that I've, when I talk to people that do this for a living with technicians that do interference hunting, they say, at least in the North American system, that these are most prevalent. And these include cell phone boosters, which anybody can buy online or at your local electronics store, cable TV leakage from cable TV systems, DECT phones or digital cordless phones, and aircraft hazard beacons. So I'll have just a short discussion on each one of these and how you can find them and how you can their existence and issues that you need in terms of being able to localize and find where they're being generated. But interference could also be generated internally. It could be, when a system is set up and deployed, there could be optimization issues, system software problems, incorrect frequency assignments, or even the hardware. Say an antenna at a transmit system is tilted too high, and maybe it's propagating further than the operators had intended, and is getting into other systems beyond the network in which the operator is authorized to use. So there could be a lot of different issues. And one example, which I'll mention in a slide or two, is cable TV, CATV systems, and there's a little diagram. These are generally about 6 megahertz wide, and in North America, or really all over the world, they're operating in quite a different multitude of frequencies, anywhere from lower frequencies, a few hundred megahertz, all the way up to, I've seen up to 1 gigahertz. So these systems are very prevalent in leakers, and if you look at a pattern on a spectrum analyzer, and you see something like you do in the bottom of this chart, you have a pretty good idea that you're looking for cable TV leakage. And then there's a whole different way you can approach the interference hunt once you say that there is cable TV leakers. Because a lot of these cable TV problems are prevalent in neighborhoods. They're deployed in the neighborhood at the same time, so they tend to go bad almost at the same time. So you can see multiple leakage points, where different connectors wear out, and you find that radiation does leak out. So one of the issues is, as I mentioned, with deployments of transmission systems, is on-channel interference. And you see a little diagram, kind of little cellular structure on the bottom right. And I highlighted in yellow number 1 as being, say a certain frequency band. So you're looking at, somebody deploying these systems, maybe in a mid-size area where there, say there's, hundreds of cell sites, and say each cell site is multi-sector, 3 or 6 sectors, maybe 4 carriers per sector. And you're talking about a lot of different radio systems. So the chances are exponentially larger, in these multi-tiered, deployed systems in cities where you could have an incorrect frequency or incorrect setup where you're generating interference. Also, as I mentioned, the antenna tilt, hardware-wise, could be a problem. There could be firmware issues in the site, and basically anything in terms of the optimization and setup of the site, can potentially be a cause of an interference problem. Cell phone boosters, a very big problem. And again, like with most electronics, there's good electronics and bad ones. And sometimes people will maybe save a few dollars and buy a cheap booster that maybe tend to oscillate, or maybe even oscillate more than they amplify in some cases. So you can see these in cars, mobile systems, homes, businesses, and if it's in a mobile system, it could be quite difficult because they could be driving, say, up to close to a transmission system, and there's overload caused that caused oscillation, and you see these spikes in the spectrum, caused by these boosters. And also with proximity, a booster is too close to a cell site, or maybe somebody has it in their home, and then a new site is deployed nearby, and again, you could have problems because of that. And again, in at least the North American market, we've seen this as being one of the highest problems of interference causes. I mentioned previously cable TV leakers, and what we show on the bottom there is kind of a spectrum, and this is, I believe this is a North American band, and so you see basically there's a lot of overlap here with cell phone systems with cellular networks, and the problem is that ideally the cable TV is closed, so it's wired, but again you do have a lot of leakage. Things get old, and you have a lot of problems in given neighborhoods. And the problem here is that you really need a system to find these leakers that are capable of identifying multiple emitters simultaneously. Because you could have in a neighborhood, maybe 4 or 5 different emitters, potentially on the same frequency, and they're all leaking. So a traditional system, if you use say a Yagi antenna and you're looking around, you could look at one direction, find a leaker, look at another direction, you find the same leaker. What do you do? So in a system that I'll be talking about, there is a special mode where you could, basically do a different kind of interference hunt, where you're not just driving towards an interferer to locate it, but you're driving a grid in a neighborhood. So you drive the grid, there's markers put on the map, this is where each leaker exists. So it's a different kind of system, and you need to be able to be flexible in your interference hunting system to be able to accommodate these kinds of very, very common types of leakers. Another one I wanted to mention, this is very, very common with digital cordless phones. And there's again, I'm showing a spectrum where the PCS in North America, uplink and downlink, and very, very common. You'll have people from other countries moving to this area that bring along their digital cordless phones. And you can see, well, if you're from Europe, you're going to cause problems. If you're from Japan, China, different areas, and you bring your phones into this area, you're going to be causing problems. So this is again, is very, very common. Very often people do this when they migrate, to different geographic areas. So it's something that really needs to be considered and kept in the back of your mind as you attempt to initially identify the interferer. So what I'd like to touch on now is some traditional methods for interference hunting, and these work, but they can be somewhat time-consuming and potentially somewhat inefficient, particularly if you start looking from an interferer from a great distance from where the interferer actually exists. And what I have on the bottom here is a chart, and what's done here is you see each little orange square identifies the position where someone is standing, and they basically rotate 360 degrees with a directional antenna and looking for the highest amplitude, the highest power level. And once they find it, they take a measurement, and that measurement is identified on the map as a bearing, that orange line. And typically you need, usually at least 3+ bearings in order to have an intersection point where you can say this is an area of probability where the interferer is being generated from. The problem is, well, if you're in an agricultural area, not a lot of different terrain issues, hills and that type of thing, it can be relatively easier to use this kind of a system. But again, you have the issue of multipath. I'll touch on this in a second. But with multipath, you have a broadcast signal that will bounce and be reflected from various obstacles, buildings, hills, cars, really anything out there. It can reflect and then come out the position where you're measuring from different directions. So if you're looking in one direction and say the interferer is you think is highest, but it actually could be coming from 180 degrees in the opposite direction. So what you need to do is you need to take multiple measurements from multiple positions. You're driving around, you need to get away from your car. You don't want the car to affect your measurements, and you need to take multiple measurements in order to get a initial fix. Once you have your fix, then you need to successively approximate. So you need to get a little bit closer, do that same process again until you hone in on the interference system. Now, if anyone has done this in Bogota or San Francisco or New York City, this is going to be one major problem with all the buildings and potential obstacles. And potentially you could do something like move to intersections and kind of do your dance and look for interferers at that point. But again, it's very, very difficult, and particularly in urban environments, to use a kind of a directional approach to finding interferers. So I mentioned multipath. So probably most of you out there are familiar with multipath. So I'll just give you a very, very high-level overview. And especially in urban environments, it's a very nasty problem. So signals from a broadcast tower will be generated and broadcast in different directions. And a lot of these components will bounce off of obstructions on its way to the receiver. So it's just a little diagram on the bottom left, see transmitter left, receiver on the right. And you can see there's one clear path potentially with the purple path, and then there's others that are bouncing around. And people in the middle, I'm sure, are using their cell phone boosters so that you can just add to the mix of different types of problems. And also, in addition to a direction problem in terms of identifying where it's coming from, you have amplitude issues, and that's kind of shown on the bottom right. So in this particular situation, you have two signals. The two here, I'm just letting them be sine waves, and they're 180 degrees out of phase. So they basically subtract and you come into a null. Which is that the result is that little bottom line. And or they could be 90 degrees out of phase, 20 degrees. So they'll, as you move maybe a few feet in one direction, a little bit over here or there, you'll see the amplitude, bouncing around. So you need a way to kind of automate that process to kind of, if it's averaging that you do, to kind of mitigate that interference, to come up with a kind of a sum total averaged in order to get a good fix on what the amplitude is. And doing that manually can be very difficult. It can be inefficient, and doing this mobily is very, is a lot more efficient and very cost effective from a kind of return on investment perspective. So here's kind of the crux of the presentation here. With that background, what I'm basically want to identify as causes and issues, and then what I kind of propose here is kind of a solution that we in Anritsu are proposing that can alleviate a lot of the different issues. It's multi-purpose. The same tools you use for mobile interference hunting, you could also use for your preliminary identification problems. You can have demodulation options. You could do signal analysis. You could do many of the different things that you need to do in an overall interference hunt with one system. So you don't need to buy one instrument here and then another kind of instrument there to do different types of interference. So you want to take your last step, you want to take out your directional antenna, you can use the same system if the conditions apply. So it's very kind of elegant solution. So you see kind of three pictures there, and it's kind of the sum total of the system all in one. So you see on the top left the antenna, and what we're using is an omnidirectional antenna. I'll get to that in a second. It also happens to have integrated a GPS antenna, so it's RF plus GPS. The GPS is used in the system to identify where you are as you're driving, and I'll show why this is needed in a second. On the big picture, you see the person driving, and I don't know if you can see in this picture next to his right arm is a spectrum analyzer in the passenger seat, and it just uses a seat belt to secure it to the seat. And the spectrum analyzer is doing some of the measurement computation as well as taking measurements, and then it's wired via USB cable to the picture in the bottom right, which is a Windows tablet. You can use a laptop or any PC, but in terms of user-friendliness, the tablet is kind of optimal. Windows 7 or Windows 8. Windows 8 is kind of good for the touchscreen capability to make it very, very user-friendly. So that's really the heart of the system. The antenna, spectrum analyzer, and tablet, and basically software that runs both, or some of the firmware in the analyzer and the software that runs in the tablet to provide a kind of elegant solution to deal with your interference issues from start, from identification to approximate localization to the actual pinpointing of the interferer. It's one system that does all these things. And the other issue I wanted to mention about the antenna, it's off the shelf. So this basic antenna here operates from, I believe it's 700 megahertz to 6 gigahertz, but you can get another antenna, maybe you want to operate in VHF or lower bands. The system works anywhere, depending on the spectrum analyzer. It's possible to go from 9 kilohertz to 43 gigahertz. If you want to look at backhaul issues or whatever, you just need the appropriate antenna and the spectrum analyzer, and you're all set to go. So looking at the hunting approach, Again, I'll just talk very briefly to the two pictures. The one on the left shows kind of what I just mentioned. Here we're actually showing the spectrum analyzer you see under the dash there in the picture, but you don't need to actually look at it. There's a viewfinder on the actual tablet where you can look at the spectrum with the same system that uses the map in the tablet. And again, it is connected to just a common USB cable. And on the right is the antenna. And the reason I want to show it is to give you kind of a feel for the size. You can fit it in the palm of your hand, very, very portable. So if you're operating in neighborhoods and you want to be discreet and don't want to bring up a lot of attention, this is a very good solution. And I've also seen, for example, in the European Union, a lot of the garages there, the roofs are a lot lower than they are in, say, this country in the United States or some other countries. So you need something that's very low profile. That if you're going to go into a kind of a low area like that, it'll work properly. You don't need to take the antenna down and move it. So it's really set up for one-person operation. It weighs a few pounds. Most of the other antennas are small like this. And also going along with the one-person operation, I'll give you some examples. In terms of directing the driver to the interference source, you can use things like voice prompts. So you don't have to stare at the map while you're driving towards your interference. You can, hear a voice, from your tablet saying left, right, or whatever. It tells you, where to go in order to find the interference. So you can use it for one-person operation. Some areas it may not be proper, legally. So you just need to check on that one little caveat, for any of the lawyers out there. But in many cases, if you can go, with one person, this system allows you to do that. And so we'll look at omni radiation. Very, very simple. You see on the left, and the simplicity is really the good part of the system. So it's really, no matter which way the radiation is coming towards your antenna, it's received identically. So it works on kind of the system works on the power of a arrival system. So it's based on the signal strength. It's the classic textbook, 1 over the distance squared, with a proportionality constant, and that proportionality constant is part of our IP. It varies according to terrain. If you're in urban, rural, or in between suburban areas, that constant may vary to optimize things. And benefits of, as I mentioned, with the omnidirectional, it's inexpensive. That antenna that we're looking at here, you can buy from your electronics store for maybe $100. You can get more sophisticated ones for a few $100s. Very simple to use, readily available. It's off the shelf, and the power of arrival system in general gives you relatively good performance in multipath environments. And since a lot of people look in cities for interference, it's a good solution. And one thing I wanted to mention is that I know you may be asking, well, if you use power of arrival, well, how do you actually identify the interference source? Don't you need a directional antenna? And the answer is basically no. So you look at the direction in the bottom, in the picture in the bottom right, and it's just a little model with an orange car going down the street, and an interfere, shown by the red dot. And so you're driving there. Well, yes, you measure, say you're measuring like minus 60 dBm signal strength, but that interfere, if that's the only information you have, it could be on the left, or for that matter, if you're just starting there, it could be on the bottom or the top, or where that street where the driver is. So you really don't know the direction. You just know the power level, with that one measurement. But the way the system works, so you get to that intersection, and you'll see that double arrow shown in blue. And the system will tell you to go left or right. So you take a choice, you may go left, you may go right. If you go left, the system will reverse you and bring you back, but it's gaining more measurement points while it's doing this. So it knows basically that as you were driving at that point in time, where the orange car is, that the red dot is not on the left, it's on the right. So you're already localizing the position of the interference by using a power of arrival system. So it's kind of an elegant system, and it has a lot of potential upsides to it, and the real downside is basically we don't see it at this point. Potentially, if you're dealing with no obstacles, no multipath, which is a very rare situation, the system may be identical to a directional system, but otherwise it's kind of an elegant system. And then in terms of value, there's a lot of good things about it, which I'll get into in a second. So just go through this real briefly. The part number you can see there for the software that's used in the system, and then the other main components: spectrum analyzer, off-the-shelf magnet mount RF with integrated GPS. Or if you don't have integrated GPS in your RF antenna, you can get a separate one. They're less than $100 in most stores. And then Windows tablet, recommended Windows 8, for the touchscreen capability. And the way it works, it's very low profile. So you see in the picture there, in the middle picture, it's kind of a cup holder type of holder for the tablet. So you just put that in the cup holder of your vehicle, position the tablet so it's right in front of the dash, so it's not obstructing your windshield. So you can just glance over and look at the map whenever you'd like to, or look at the spectrum, or the interference parameters that'll show you in a second. Or you can get suction cup mounts that just go right onto the dash itself. So it's below the line of the windshield, but it's very easy for the driver to see, if you choose to go to a one-person operation. So why use a mobile interference hunter? But so mainly, we're kind of just touching on that as we've been going along. So the manual process can be very time-consuming, very inefficient. Look at the diagram on the left. Say that transmit tower. Let's just say that's an interferer. In your car, and you look at, if you look at a directional antenna, it's coming from all over the place. So you really got to take a lot of different measurements in a lot of different areas to be able to mitigate that multipath effect. So what's important in a mobile interference hunting system? So by mobile, I mean a system that's located in a car vehicle. So RF antenna, we kind of looked at, you want something small size, you want something inexpensive, hopefully it's non-proprietary, that you can get off the shelf. Something portable, something mag mount that you can take off when you're not using it if you desire to do that. You can move to another car. You can set the system up in a compact car as well as a van. So it works pretty much in any type of situation. You want a multi-purpose spectrum analyzer, something with high dynamic range. You can see the low signals in the presence of the large signals. You want something with a lot of the options. So you don't want something just for the interference hunt while you're mobile. You want something that you can identify the interference with. You can do quality analysis. You can look at the kind of signal it is. You can look at the history of the signal and many other things to get you a major head start in your interference hunt, which is pretty crucial. And you also want something with in touching with a dynamic range, a good noise floor. And why is that important? Well, you can start your interference hunt a lot further from where the interference exists. And some of the hunts that I've been doing, or we've been doing in San Francisco, for example, you can start your hunt from a couple of kilometers away, depending on the signal level of the interferer. But it's a great advantage because if you can start a lot further away, you save a whole lot of time in your interference hunt. You also want something that's easy to use. In this system, the setup is typically less than 5 minutes, and you can also, most of these settings are remembered. So if you want to have a certain, say in your spectrum analyzer, a certain RBW, resolution bandwidth, video bandwidth setting, if you want to keep if you need a preamp, keep that on. You turn your spectrum analyzer off, you turn it back on the next day, your settings are remembered. Same thing with the tablet, the software. Many of the settings are saved by the user, so it doesn't require a lot of new setup. If you do a new setup, we're talking about maybe 5 minutes. To reuse setups, maybe a minute or so to really from when you get started, get out in the car until when you start rolling and start your interference hunt. So the other thing, and I just won't touch on it again, is it's the ability to locate different interference signals. So we'll look at pulse signals, and one of the things you can do with a spectrum analyzer that may be difficult with other systems is to do something like set up a max hold system. So you're basically triggering and taking a measurement while that signal exists. So you can maybe say if it's up 1 second and off 5 seconds, you can maybe take a measurement every 6 seconds. What is the maximum? And that is, when it's pulsed. And then it just keeps taking the maximum. And then as you drive, as you're going towards the interferer, that pulse will grow in magnitude or power level, as you see on the spectrum analyzer. So it's a feature with the spectrum analyzer that really gives you a good capability with this type of signal. And we'll also look at a signal, how do you find signals in LTE uplink bands? And it's not as easy as one might think, because there's a lot of traffic in that signals that should be there, with people talking, that it may hide the interference signal. So I'll show you a short 10-second video that shows you another feature that you can do with a spectrum analyzer called min hold, where you can identify signals in traffic channels, and especially with LTE, a lot of people want to look in these kinds of channels, when they're looking for interference, because it's a very important system because of the expectation that customers have. And then also very, very, very important is being able to have a channel bandwidth power measurement. So signals that drift in frequency, and there's a lot of those signals out there, you need a channel power measurement in order to follow that signal. So what I'll do here is look at, a very important, kind of a band where we need to find interference, LTE uplink. And it may not be clear on this picture, but you can look at 3 different colors. The green is where a max hold is set. The yellow trace there is the live signal, and the blue is a min hold. So you can see that little spike underneath of the live signal is your interference. So it's really quite obvious to see. So I'll keep my fingers crossed here. This is a little video, so hopefully it works okay. And what you see right now on this chart is a traffic signal. This is LTE uplink. And there is an interferer in that, but it's really impossible to identify unless you have a minimum hold capability on your spectrum analyzer. Okay, as you see, the signal is still traffic. Now you see on the right, you're moving to min hold, and you see all the traffic is going away, and you're left with your interference signal. So that's just kind of a little demo. And in this system that we're talking about today, the user can set up the time. So you may set up like every 2 or 3 seconds, you do a min hold, and you capture your interference. You eliminate your LTE traffic from consideration, and then you reset it automatically, and then take a measurement again. So you're constantly looking just at the interferer. So if you're looking at this kind of system, this is almost essential unless you have a very sophisticated kind of algorithm to remove the traffic. But here we really don't like sophistication. We like simplicity, because it's more bug-free and it's easy to use, and it's more efficient for the user. So you don't need a lot of training in order to operate this. So key specifications. So what kind of spectrum analyzer do you need? Well, I mentioned good dynamic range, something typically better than 100 dB, a fast sweep. And just give you some typical parameters here. So if you're looking maybe in a 1 megahertz band with a 1K RBW, and a certain noise floor, a certain number of sweeps per second, would be satisfied. It's just a rule of thumb. Doesn't mean you have to have this capability, but you need something that's fast enough in order to accommodate the system. I already mentioned channel power measurements, for your frequencies that drift, preamp capability, and what this does for you, it gives you a better sensitivity. You have a lower noise floor, you can get maybe 10, 15 dB of improvement. What does that mean? Again, it means you can start your interference hunt further away from the interference source. So you can see it much more quickly, and once you can see it, you can start hunting the signal. And I mentioned also earlier in the presentation, save an event. One innovation that we have is something called burst detect, which you could basically call something like receiver mode. So if you want to locate a very, very fast pulse signal, and so this kind of measurement becomes critical. So this something you might be able to see with cell phone boosters, which I mentioned is kind of a common type of interference source. So what this receive mode or burst detect does is use FFT, fast Fourier transform technology to capture a span as wide as 15 megahertz simultaneously, up to 20,000 measurements per second. So this gives you, the ability, in some of our analyzer models to capture that very, very quick burst, which some of the operators and people involved with, wireless, find important. So that's another consideration to look at when you're, looking at, spectrum analyzers. So with a mobile system, as I mentioned, in general, you need something that can mitigate the multipath. You can do a lot of average measurements, and it's something that needs to be ideal or optimized, or can be optimized for hunting interference in urban areas. So I mentioned the channel power. It's important for finding the wideband signals, but it's essential for finding signals that drift in frequency over time. Some other features we're looking at are voice prompts for one-person operation, min-hold, max-hold we talked about, and others we also talked about. The other thing I want to mention is sensitivity settings. So there's a setting in this interference hunting system where you could optimize for your environment if you're in an urban area or if you're in a rural area or anywhere in between. You can optimize the system to mitigate the multipath in the best way possible to be able to find your interference as quickly as possible. We use maps here on this system. They're provided by Google Maps or OpenStreetMaps. They're both free of charge. With Google Maps, you just need to have an internet connection during your hunt. So you can use like a USB modem, for example. You just need to make sure that the frequency of the modem is not interfering with your actual hunt. OpenStreetMaps, we have a web page. We have thousands of cities. You can download already made maps, or we can step you through the three-step process to make your own map. So this is the hunting system. This is what you see on your tablet. And again, the top chart is your power versus time or position. So you start your hunt on the very left, and as you drive, there's our car icon on the map that moves as you drive, so you can see where you are. And then the power that you're measuring is measured or shown on that power versus time. So the amplitude or the height of the rectangle on that chart is proportionate to the signal strength. Also in this, you see little gray circles. So once you accumulate enough measurements, a little translucent gray circle appears on the map, and that directs you to the area of most probability of where the interference is located. Also, you see what we call little breadcrumbs. So as you're driving, it leaves little colored dots in your wake, and those colors are proportional to that chart you see on the top right. So as you get closer and closer, you start moving from the black all the way up in different colors towards the green. So as you do your interference hunt, you can look back and see, well, I found a peak over here and a peak here, so maybe you want to go back and do a little more searching over here, and you can look at all your breadcrumbs, and it gives you multiple ways of identifying, where the signal strength is highest. It does all the different averaging and different proprietary algorithms that affect the hunt. So what I'll do is this hunt is about 3 or 4 slides. I'll just skip through, but this is a typical interference hunt. So this is taken in the financial district of San Francisco. So lots of multipath. So you can see the car there, and where it says vehicle position. So and you see the top power versus time chart on the top. That's that yellow line, that vertical line. That shows you position on the chart. So you drive along, you move along the chart. And you can see you're eventually going to your interference position. You can see next to the power versus time, that little yellow bar chart. It's a little power chart to give you instantaneous power levels. You can see that. And you're also able to look at the spectrum. So by double tapping on this map, you can actually bring up the spectrum if you want to look at that for any given reason. You just tap it again and it brings up the map. Sorry. So once you get, close to your interferer, you want to take that final step. And why is the final step required? Well, the interferer could be on the top of a building or on the 5th floor of an office building or somewhere. And obviously you can't bring your car, to pinpoint it. So you get up close, and then you can pinpoint it with a Yagi or log periodic type of directional antenna. And here we're looking at what's part number is MA2700A. It's basically a tool. It's not just a handle. It has integrated GPS, preamp, gives you great matching for your antenna, and also a better sensitivity, as well as a magnetic or electronic compass. And this compass basically tells you the azimuth or the direction. So as you're doing your 360-degree turn to find the amplitude peak, it automatically identifies the direction that you're pointing. So this couple of slides where you can't use the mobile system, where you need a portable system, with a Yagi or log periodic. So, again, if you're in the top of a building, you could have shadowing effects here where, you could be very close to the building and may not get as good a signal as you are as if you're further away. Could be on the top of a building, or it could be, you're not able to get close to it, drive close to it because it's fenced off or, there's no trespassing or whatever reason. And if it's indoors, one thing that you can use, it's another option that we have available on our spectrum analyzers. And again, it's a good reason to use a spectrum analyzer in your hunt because you could use so many different things with it in your interference hunt. But you could do a coverage map, so you're looking at amplitude as you just walk around indoors to position you close to where the interferer is. You don't have to use it, but if you use a directional system, you can also use that with the spectrum analyzer. It just, sometimes the reflections inside can be daunting and could be an issue. So for pinpointing, we're looking at, as I mentioned, this is a picture below on the top left of the Yagi antenna. It's very directional, but narrow bandwidth. So you may only get tens or maybe 100 megahertz bandwidth from it. Log periodic, you can get gigahertz worth of bandwidth, but the beam width is broader, so it's not as directional when you're trying to pinpoint something. And again, we're showing the InterferenceHunter portable version, so it's a tool that you can go for the final step for identifying the interferer. So to summarize, we'll go through is for the mobile hunting system, it's something that it can save users time and money. So it's very efficient in locating interferers. From all the steps right into you just about pinpoint the interferer. So you want to find out whether it is interference. Approximate the interferer position, and do the hunt with a one-person operation, very efficiently with the off-the-shelf magnet antenna, voice prompts. There's also tones that can be played, so you can play a tone in the car that goes up in pitch as you get close to the interferer. So there's different ways depending on the user preference to direct the driver to the interferer. There's also, if you want to use the map and look down on the map occasionally, there's green arrows that point you, where to turn in order to, get closer and closer to the interferer. So, you want a good spectrum analyzer that's multi-purposed. It can do demodulations. It can have, has a preamp. It can do channel bandwidth, min and max, power, captures. With something, good off-the-shelf, inexpensive, non-proprietary on the antenna, voice prompts, one-person operation. You want something that's multi-featured, all types of interference, all types of environments, and it can give you a complete and comprehensive system. And a little advertisement, sorry, but there it is, bottom left, if you're interested in finding out more. Okay, thank you.
Thanks, Mark. This is Kyle again. We've had...
Hey, Kyle, I guess, any questions?
Yeah, we've had quite a few come in. We'll get to them as quick as we can. We're running out of time here. But the first one we had come in Does the 2000 1645R, 1646R, or 1646R antennas have the GPS receiver in them, or does one need to also have the 1647 for integrated GPS?
I don't have the part numbers committed to memory. I know the one that we showed does have integrated GPS. I'm not aware of any antennas that we offer that also have it, but not to, I can't give you a definite answer. Let me just look at, I have a little page here to look at. I don't believe so, but I can get back to you on that. One thing I did want to mention, though, that your receiver does need option 31 in the spectrum analyzer. That's one of the options. So in using a GPS antenna, obviously you have the antenna, but you also need something on the receive side. So I did want to mention that, people interested in looking further, can see that.
Great. Another question we had in is, what is the average time to find interference using the Anritsu mobile interference system?
It really depends on many factors. It depends on your geography. If you're in an agricultural area or in an urban environment, it depends on the type of interferer that you're looking for. In my experience, once we're able to see the interferer, we've done a number of interference hunts in San Francisco, for example. I'd say about 20 minutes or so to be able from where we first saw the interferer to being able to identify the location. In rural areas, it's quite a bit quicker. We've done hunts in suburban areas. It's generally, generally less than 30 minutes, unless there's, something unusual, going on. I have seen in other cases, and just talking to operators, that some of these hunts can take as long as 2 or 3 days. Not with using this system, but in traditional systems, and sometimes they're never able to find the interferer. If it's periodic in nature, or it's only there some of the time, it becomes very, very difficult to find it. So again, the bottom line answer is really it depends.
Great. We have time for just about 2 more questions. Another one we had come in: will the spectrum analyzer and BTS SiteMaster work?
Well, that's a kind of sure it works. With the system, yes. Sorry, a little humor there.
Yeah.
Yeah, it will work with the system. On the website that had published there, we have a list of all the analyzers that the system will work with, and pretty much every analyzer that we offer, and some that we no longer offer that maybe people have already purchased, will work with the system. And the other thing I want to mention with that is that there's no firmware upgrades needed. So just as is, it will work.
Great. We have time for just one more question. Do you see any sort of advantage between using Google Maps versus OpenStreetMaps?
If you're not operating in the frequency, with your modem, Google Maps can have an advantage. So as long as you're not interfering with the interference, the only issue there is that whatever cost you have for data rates. But if you're working, like say, for a cellular provider, it may not be an issue. But so you are talking back and forth to the Google server, for updating maps and that kind of thing. So just keep that in mind. OpenStreetMaps are generally free as long as you capture the area that you intend to hunt, and you can make it a large area. There's no issues. So I think in general, particularly if you're not working with a cellular provider, that potentially OpenStreetMaps might be a bit better.
All right, great. That's all the time we have for today. I want to thank everyone for attending. Mobile interference hunting, a unique approach presented by Anritsu. Again, our presenter today was Mark Heimbach, Senior Product Manager at Anritsu. Thank you, Mark.
Thank you.